All right, we're back. We're on page 2 of math analysis. Nope, sorry, Calc AB, not math analysis. Calc AB Notes 5. We're talking about the mean value theorem, MVT. Huge, important idea. Going to come up all over the place. So let's take a look at what it says exactly. And then you're going to memorize what it says exactly so that you can use it exactly the right way. So the mean value theorem says if the function f of x is continuous on the closed interval. So continuous closed, and then differentiable on the open. So differentiable open, continuous closed, differentiable open, continuous closed, differentiable open. So you don't need it to be differentiable at A and B, or A or B. You don't need to be differentiable there. You just need to be continuous. Continuous on the closed interval, differentiable on the open. So it's got to be differentiable on the open. As long as that is true, if the function is continuous on the closed interval, differentiable on the open interval, then there exists some C such that f prime of C, so C is between A and B, f prime of C is equal to f of B minus f of A or B minus A. So keep in mind what each of these things is, right? So f prime of C is slope of the tangent. And then f of B minus f of A over B minus A is the slope of the secant. So the slope of the secant equals the slope of the tangent for some value between A and B, as long as you're continuous on the closed, differentiable on the open. So we're going to have to state that a lot. So make sure that you remember that. Continuous closed, differentiable open, say it with me, continuous closed, differentiable open, continuous closed, differentiable open, continuous closed, differentiable open. Just keep saying it over and over again. And then as long as that's true, slope of the secant equals slope of the tangent, slope of the secant equals slope of the tangent. You just say it a lot, just keep saying it. All right, so let's do the first problem on the page, which it turns out is saying what needs to be true for the mean value theorem to apply. Is it possible that you don't remember? I doubt it, but maybe. So what we need is, we need f of x is continuous. Ugh. That's like my least favorite word to write all the way out. Continuous on the closed. So I'm just going to say on the closed interval AB, continuous closed and differentiable on the open interval AB. So it's all right if you're differentiable at A and B. In fact, it's probably preferable, but it doesn't need to happen. You just need continuous closed, differentiable open, continuous on the closed, differentiable on the open. Could it be differentiable on the closed interval? It could be, right? You're going to use a ton, in fact. It's often going to happen. But it only needs to be continuous on the closed interval. So keep that in mind. If you can't tell, I'm repeating it over and over because it's like super important. All right. The function f is continuous. It doesn't say differentiable. Function f is continuous with f of -3 equals 1, f of 5 equals -7. If the MVT applies, which we have no reason to know if it does or doesn't yet, use the graph of f prime to approximate the values of x satisfying the, okay, so now this is more interesting because we have the graph of f prime. So this is f prime right here. We have the graph of f prime, and the graph of f prime shows you that the derivative does in fact exist everywhere between -3 and 7. So I'm going to say, since f prime of x exists for all x element of -3 to 7, and I could include -3 and 7 because it also exists at those points. I mean, this is the graph of the derivative. You're looking at it. The derivative itself is not differentiable at -2, at 0, and at 3 because you have sharp turns there. But that's not the question. If the derivative exists, then the function itself is differentiable. So since f prime exists for all x between -3 and 7, f of x is differentiable on -3, 7. So it's differentiable on the open interval. It's given that f of x is continuous, I think. Yeah, is continuous therefore continuous on the closed interval, -3 to 7. All right, so therefore by MVT applies. So so this all means, let's say, so this implies that MVT applies. Okay, so therefore f prime of c, oh god, that's not a c at all. What is that? F prime of c equals f of b minus f of a. So I'm going to say f of, you know, I'm doing the wrong problem here. I need it to be -3 to 5. The whole argument works. I just got to change all these 7s to 5s. Turns out, you know, it's good to let me know that, everybody at home, not saying anything. All right, there we go. So I'm just going to use f of 5 minus f of -3 over 5 minus -3. All right, and what does that work out to numerically? -7 minus 1 is -8 divided by +8, so is -1. And then we'll say for some c element of u. So it's got to be on the open interval, -3 to 5. Okay, so now let's hunt for those. All right, so where does this thing, you know, the question is weird because it says approximate the value, but I'm pretty sure we can find the exact values, so I'm not sure why it's saying approximate, but whatever. I think a very good technique when you're doing these problems, we're looking for where f prime is equal to -1. Let's draw a line. It could be a solid line, it doesn't matter. And we're looking for the intersection, so here and here, we just need those x coordinates. So I'm going to say, that's definitely -4.5. So c equals -4.5 and c equals 0 are the values of c. So what are those values of c? Guaranteed by the mean value theorem. So let's write it. You know, I should guaranteed by MVT. You can abbreviate mean value theorem as MVT. You don't even need to put the periods, but I'm putting them. So those are the places where the slope of the secant, those are the values, they're really x values. They're the x values at which the slope of the secant line equals, where this, sorry. Let me start again. Those are the values of x at which the slope of the tangent line equals the slope of the secant line. The secant line is from x equals -3 to x equals 5. -3, oh my god, could I mess this up even more? So since I'm only looking -3, man, this is crazy. Okay, -3, I'm only supposed to be looking on this interval. So what has happened here? I've got an extraneous solution, which is also really common. I almost fooled myself. In fact, if I hadn't gone back to like talk to everybody about it, I definitely would have. So I'm going to delete this or erase it. I don't know what it's called when you're handwriting on a computer and then you have to get rid of something. So I'm going to say is the value. So there's only one. So x equals 0 is the only value of x in this case at which the slope of the tangent line equals the slope of the secant line on the interval from -3 to 5. So I think in the end we got this right. A lot to think about, right? So we needed to be continuous on the closed, which was given, differentiable on the open, which we were able to infer from the fact that the derivative exists everywhere between -3 and 5. So we met the conditions of the mean value theorem. Mean value theorem says if you meet the conditions, then the slope of the tangent line somewhere between -3 and 5, maybe multiple places, maybe only one, the slope of the tangent line somewhere between -3 and 5 will equal the slope of the secant line from -3 to 5. So we set up that equation. We found that the slope of the secant line is -1. We went searching and we found exactly one point, because that other part didn't happen, exactly one point where it was true, and that was when c is equal to 0. So we answered the question. Good for us. That's our first mean value theorem problem that we've done. This is one of the most famous pictures in all of calculus. It's a very clear indication of the mean value theorem in my mind. So I think that we'll just stop here with you kind of looking at it, right? So I'm going to highlight the secant line. So we're saying, here's your secant line. And then you are able, guaranteed in fact, to be able to find 2 parallel tangent lines. In this case, you're guaranteed to find 1 parallel tangent line. You might find multiple. You could find 50, you could find 1,000, like who knows. All right, I'm gonna cut this video here. I'll come back in the next video and we will keep going. So I will see you then.